Hey, geometry. We are going to work through lesson 11, unknown angle proofs. We're going to break it into proofs of known facts. You may hear some grumbling in the background. I'm in the geometry classroom today, and we can hear the tinkering studio in the background. So I apologize for that, but it's hard to find quiet places when I'm at school. So, first of all, what is a proof? I know this is day 3 on proofs, but let's talk a little bit about what a proof is. A proof of a mathematical statement is a detailed explanation of how that statement follows logically from other statements already accepted as true. A theorem is a mathematical statement with a proof. So that's just a little bit about what a proof is and what a theorem is. We've been working through proofs, so detailed explanation of how a statement follows logically from one statement to another, and most everything that is already accepted as true. So in the previous 2 lessons, we've done proofs, and we've made statements, and we've given explanations as to why, but everything we've used as far as statements, they're already accepted as true. Like, if you have 2 parallel lines and a transversal, we have accepted as truth that alternate interior angles are equal in measure. Okay, we've accepted as truth that the interior angles of 2 parallel lines with a transversal, if you add them together, you get 180, so they're supplementary. Those are already accepted as true. A theorem is a mathematical statement with a proof. So let's erase this. I also want to point out at this time that, theorems are often written as if-then statements. You guys have learned about if-then statements in science. So they're if-then statements, which you have if your hypothesis, then your conclusion. So that's what we're going to be doing. All right. Once a theorem has been proved, it can be added to our list of known facts and used in proofs of other theorems. For example, 2 lessons ago, we proved that vertical angles are of equal measure. Remember, these are vertical angles. And we know from earlier grades and by paper cutting and folding that if a transversal intersects 2 parallel lines, the alternate interior angles are of equal measure. How do these facts help us prove that corresponding angles are equal in measure? So in the diagram to the right, we're going to work on this. You are given that AB is parallel to CD. How can you use your knowledge of how vertical angles and alternate interior angles are equal to prove that X is equal to W, to prove that those are corresponding angles are equal. So when I get to a proof where I don't know where to start, I just start writing down what I know. So I know that angle X is equal to angle Y, and angle Z is equal to angle W. And I know this because they are vertical angles, and they are equal in measure. Awesome. Okay, what else do we know? Let's talk about the alternate interior. So we know that angle X is equal to angle Z because alternate interior angles are equal in measure. Okay, let's look to see if we can do anything with this. Okay, I always go back to what am I trying to prove now? I'm trying to prove that X is equal to W, and those are all the X's and W's I see. What's cool here is I have z equal to w and x equal to z. So those are the same, and I'm trying to find x is equal to w. I think I've done it. So I can now say that x is equal to w because of substitution. Substitution. You can also say the transitive property, which we've already talked about just a little bit. They're very similar properties. Cool. So we have the following facts. These are in our pocket of tools. Okay, our facts that we are able to use all the time are vertical angles, alternate interior angles, and now we know that corresponding angles are equal because we just proved it. So those are things that I can say without further proof because I've proved them in the past. And that's just what we said. So we have these available facts. Vertical angles are equal in measure, alternate interior angles are equal in measure, and corresponding angles are equal in measure. Use any or all of these facts to prove that interior angles on the same side of the transversal are supplementary. Add any necessary labels to the diagram below, then write out a proof including given facts and a statement of what needs to be proved. Okay, so given AB is parallel to CD, transversal EF, we want to prove that the measure of angle BGH, we're going to say that's X, plus the measure of angle DGH, we're going to say that's Y, is equal to 180. Okay? Okay, I'm going to label some other angles. I'm going to say this one is A, and that one is B. All right, so let's go with this. I'm going to start writing a little higher. So we know that AB is parallel to CD because it's given. Okay, I can also say that angle A plus angle X is 180 because linear pairs are supplementary. And then I can say that angle A is equal in measure to angle Y because they are alternate interior angles. And then once that I know that angle A is equal to angle Y, I can say that angle Y plus angle X is equal to 180 because of the substitution property of equality. Okay, I go back. What are we trying to prove? GBH, which I labeled X, and DHG, which I labeled Y, is equal to 180, which I just did. So now that we've proven it, I can add it to my available facts. Interior angles on the same side of the transversal that intersect parallel lines sum to 180. Use any of these four facts to prove that the three angles of a triangle sum to 180. For this proof, you will need to draw an auxiliary line parallel to one of the triangle's sides and passing through the vertex opposite that side. Add any necessary labels, and write out your proof. So I'm going to add a line that didn't touch. Right up there. Not too bad. And I know that those are parallel. And I actually have two transversals here. Okay? So J, K, I don't know why. So we can say that JK is parallel to BC because I made it that way. But what you write is construction. Okay? Let's add some letters. Let's do little a, little b, little c. Now I can say that a plus b plus c equals 180. Okay, and it's linear pair. I know it's more than a pair. Sum to 180. Very cool. Okay, now let's use some of the tools that we've just proven. Let's see, I need my highlighter. If I have parallel lines and a transversal, I know that this angle is equal to that angle. So let's do that. Goodness, I need a letter here. A, B, C, D, and E. I don't know why. So we know that angle C is equal to D, alternate interior angles. Rewind. So I have two parallel lines and a transversal. So alternate interior angles. Now I have two parallel lines and a transversal. I have alternate interior angles. So I can say that A is equal to E for the same reason. Now I can substitute. Okay, these two equalities into that equation. So instead of A, I'm going to write E. Instead of B, nope. And instead of C, I'm going to write D equals 180 degrees because of substitution, property of equality. And we're done. Okay, now we have another tool in our toolbox. Interior angles of a triangle equal 180. Very exciting. Okay, let's talk about this one. I need to move this, I'll move it back. Let's review the theorems we have now proven. We did vertical angles, oops, I'm so sorry. Vertical angles are equal in measure, transversal intersects, gives us alternate interior angles and corresponding angles, and then interior angles on the same side of a transversal are 180, and this should be its own bullet point. The sum of degrees, a measure, and a triangle is 180. Cool, let's put that back. All right, next thing. The question that I want to ask is, what is the absolute shortest list of facts from which all other facts can be derived? So let's just take a little side trip. Take a moment to look at one of those really famous Greek guys we hear so much about in geometry. Eratosthenes. If you can pronounce that to me very well tomorrow, I'll give you a piece of candy. Over 2,000 years ago, that person used the geometry we have just been working with to find the circumference of the Earth. He did not have cell towers, satellites, or any other advanced instruments available to scientists today. The only thing he had used were his eyes, his feet, and perhaps the ancient Greek equivalent to a protractor. Watch this video to see how he did it and try to spot the geometry we have been using throughout this lesson. I will link it. Oh, sorry. I will link it to Google Classroom. But please watch it. It's really good. Cool. All right, example 1. Construct a proof designed to demonstrate the following. If two lines are perpendicular to the same line, they are parallel to each other. Okay, so I have here, if two lines are perpendicular to the same line, they are parallel to each other. Draw and label a diagram, state the given facts and the conjecture to be proved, and then write out a clear statement of your reasonings to justify each step. Okay, I just redrew the picture so I could label it a little bit better. So we have some things that are given. I'm going to say that AB is perpendicular to EF, and CD is perpendicular to EF, and that's all given. We're trying to prove that AB is parallel to CD. That's what it says here. Draw and label a diagram, check. State the given facts and the conjecture to be proved, given facts, conjecture to be proved, and then write out a clear statement of your reasonings for each step. So let's do that last thing. I'm going to write out some little letters. Little a, little b, any other angles? Nope. Okay, so we're just going to use those. It's just easier to write the little letters than it is to write the three-lettered name of an angle. So we do know that angle A is 90 degrees, and we know that angle B is 90 degrees. And we know that because perpendicular lines form 90-degree angles. Okay? Now we know that this transitive property, I'm going to write that out a little bit different. So we have angle A equals 90 degrees and angle B equals 90 degrees. If I wrote it like A equals 90 and 90 equals B, I've told you guys a few times, if the middle matches, the outside are equal. We can say that A equals B because of the transitive property of equality. It's just one of those tools that we use a lot that is very similar to substitution, but it's not. So A and B, they're corresponding angles. If these two are equal, then you know those two lines are parallel, because that's the definition of corresponding angles. So now that I can say that segment AB is parallel to segment CD because of the corresponding angles make parallel lines. When corresponding angles are equal, then we have parallel lines. All right, so each of these three parallel line theorems has a converse. This is an important thing in geometry. A converse is the reversing of a theorem. So, for instance, if we said that if two parallel lines are cut by a transversal, then alternate interior angles are equal in measure, the converse says if two lines are cut by a transversal and the alternate interior angles are equal, then the lines are parallel. So first we say we have two parallel lines, so alternate interior angles are equal. But if I have alternate interior angles are equal, then I have parallel lines. So that's the converse or the reversing. If two parallel lines give me corresponding angles, I can also say if I have corresponding angles, then I have parallel lines. If I have two parallel lines, the interior angles add to 180. I can also say if the interior angles add to 180, then the lines are parallel. Notice the similarities between the statements in the first column and those in the second. Think about when you would need to use the statements in the second column. That is, the times you are trying to prove parallel lines. So when you're trying to prove two lines are parallel, you're using the second. If you know two lines are parallel and you're trying to use that information for other things, that's when you use the first column. This page, so this is the closing, okay? That's what we've talked about. Okay, hold on a second. All right, in the figure to the right, x equals y. Prove that segment AB is parallel to segment EF. Okay, this one's pretty simple because we just put that tool in our toolbox. So if I say that x equals y, it's given, right? Then I can say that AB is parallel to EF because of the corresponding angles are equal in measure. If corresponding angles are equal in measure, then the lines are parallel. That's that converse that we just talked about. Cool. Not this page, next page. Okay, in closing, review the parallel line theorems by stating the original and the converse of each theorem. So I would ask you to go back and look at this page. I have to go back to that page though. I'm trying to get there. Let me try again. So that's it. I mean, that's what we're reviewing. So we'll work on our classwork, our problem set tomorrow. Good job.